Take a look at the homework from last night, 453, 1 to 2, 5 to 9, 11, 13 to 16. Any issues with any of those questions on page 453, please? Yep, absolutely. We didn't assign number 12, but we can do it. Having a little bit of trouble there, Max? 214 degrees. The reason I didn't assign that is because of the notation that they use there. We don't need to be familiar with that notation. 214 degrees is always measured from the positive x-axis. This would be 0, this would be 90, this would be 180, this would be 270. So we go around here, that's 90, this would be 180. 214 would be somewhere between 180 and 214, right? So we'd add, what would it be, 34 degrees right here? Okay, that would be the momentum vector. The equivalent of 34 degrees south of west there. Okay? So don't panic about that because, again, I didn't assign that because we don't need to be familiar with that notation. But they do use it fairly often in this textbook, that notation. So it's not a bad idea to be familiar with it. Any other questions that we need to go over that we assigned? Yeah. The last two questions, yeah, 15 and 16. Was it 15, 16? Okay, 15, 16. What about 7? Anybody for 7, the Mexican jumping bean thing? No? Well, I want to go over that one anyways. One person here said yes. Any others? 7, 15, 16? Going once, going twice? All right, 7 it is. A Mexican jumping bean moves because an insect larva inside the shell wiggles. Would it increase the motion to have the mass of the insect greater or to have the mass of the shell greater? Only one person said they needed that question gone over, so that means that the rest of you must have an answer to this question. What's the answer to the question, Cameron? Yeah, that's exactly it. It says the little thing in the center because that's the thing that gives it the momentum. Yeah, it's a good answer. In the end, there's a certain amount of momentum that this object is going to have. Okay. Now, it's the larva inside that imparts the momentum to the shell. Okay, and that makes the shell wiggle, right? Do we want to have something that's heavy and therefore has most of the momentum transfer its momentum to something that's light, or do we want to have something that's light with a little bit of momentum transferring its momentum to something that's heavy? It's kind of like this. You've got a semi-truck imparting momentum to a smart car, or a smart car imparting momentum to a semi-truck. Okay, which is going to cause more movement after the collision? The semi-truck hitting the smart car, right? The heavy thing with lots of momentum imparting its momentum to the light thing. Does that make sense? We have a certain amount of momentum, okay, and we impart it to something that's heavy, or we impart it to something that's light. The light thing is going to move more because it has less mass. Make sense? How many people more or less got that? Good, excellent. Okay, that's one of those questions that's a good thinking question. Okay, you guys are in, already, I think, just a few days in here, pretty good shape when I hear you, how many people got a question like that correct, because it's not just, remember when we talked about this in class, or remember when we wrote down these notes in class? Okay, that's a thinking question. If you got that, that's really good. Now let's take a look at 15 and 16. 15 says a blue whale is the largest mammal ever to inhabit Earth. Calculate the mass of a female blue whale if, when alarmed, it swims at a velocity of 57 kilometers per hour and has a momentum of 2.15 times 10 to the 6 kilograms meters per second. One thing that I want to do right away is circle the kilometers per hour. I haven't even given any thought whatsoever to the question, and I always say do that first. But you know what? If you spot something that could lead to a really careless mistake, and you just identify that right away. You don't even have to have any idea what's going on in the question. You can identify something that's going to lead to a silly mistake, like kilometers per hour. We know we're going to have to convert that to meters per second. If you don't spot it right away, that's okay, because when you go to circle your givens, maybe you'll spot it then. But if you do spot it, then just identify it so that you don't forget later on when you're actually thinking about the question. Okay, it's a momentum question, although we have the momentum here. There's no real tricks to this other than the unit conversion. It's just, here's the momentum, here's the velocity. Okay, let's find the mass of this. Let's find the mass of this whale. So let's circle our givens here. This is going to be V, although we've got it circled in red, so we know we're going to convert it. This is P, the momentum. We're looking for mass. We're going to say P is equal to M times V. Rearrange that to solve for mass. V goes down by dividing. I get P over V. 2.15 times 10 to the 6, I think it was. Divided by the speed, or the velocity, I should say. We're going to convert that 57 kilometers per hour, though, to meters per second. How do we do that? Divide by 3.6. We're not going to forget that, right? Because we circled it in red, or we highlighted it in pink, or we, drew arrows to it, or whatever we do to draw attention to it. What is that, by the way, 57 divided by 3.6? What is it? Let's go with the unrounded number there, 15.833. Thank you. We don't want to round to 1 or 2 decimal places until we get to a final answer, okay? Let's go 4 or 5 decimal places unless it's a final answer, and then we look at the proper number of significant figures. Okay. In all likelihood, Jonathan, you're going to get the right answer still if you round it to 15.8, but there's maybe a 10% chance that you're going to be off by 1 decimal place, and if that's a numeric response question, you get the wrong answer. Okay. So what do we get when we divide those two numbers? It's pretty straightforward now that we have the conversion done, right? Yep. 1.36 times 10 to the 5, and it would be kilograms, and it would be 3 digits. Good, because both of those pieces of data are 3 digits. Okay. Is that okay? Take a look at 16. It says a loaded transport truck with a mass of 38,000 kilograms is traveling at 1.20 meters per second to the west. What's the velocity of a 1,400 kilogram car if it has the same momentum? This is a little bit of a different question. That word same means something to me. The car has the same momentum as the truck. The momentum of the car is equal to the momentum of the truck. So why don't we get the momentum of the truck and make that the momentum of the car? Does that make sense? Okay, the word same is what tells me that. Get the momentum of the truck, then set that equal to the momentum of the car, and then solve for the velocity of the car. I'm going to write down 2 bits of givens here. We'll say the mass of the truck is 38,000 kilograms. And the velocity of the truck is 1.20 meters per second. Let's just say west is positive here so that we can make everything positive, not worry about the negatives. Let's say the velocity of the car is what we're looking for. And that's all we have, isn't it? No, sorry, we have the mass of the car is 1,400 kilograms. Now let's make a prediction here. Is the velocity of the car going to be less or more than the velocity of the truck given the same momentum? More. Why do you say that? Yeah. Good. Perfect answer. The momentum has to be the same. Okay? This momentum isn't going up, it isn't going down. If the mass is less, then the velocity must be more in order to keep the momentum the same. Okay? So we know it's going to be a higher value, in fact, quite a bit of a higher value, right? Because the mass is dramatically lower. Okay, let's figure out the mass of this, or the momentum of this truck now. It's going to be mt times vt, which is 38,000 times 1.20. What do we get for that? 45,600 kilograms meters per second. Now, we got to find the momentum of the car, which we know is going to be 45,000. Let's rearrange to solve for VC. It's the momentum over the mass. And what do we get when we divide that? Somewhere around 30? 32.6? 3 digits, it would be 32.6 meters per second. We got a positive value, by the way. Positive value means here in this question it's to the west, right? Because we define west as positive. Yep, Tanner? Yes. Say it again. Yeah. 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 Yeah, that would work. But when you do that, Tanner, whether you think about it or not, you're effectively doing the same thing. Okay, Tanner says, basically, could you divide 38,000 divided by 1,400 and then multiply it by 1.2? Absolutely. What you're doing there is finding a ratio, right? And that works because it's a linear relationship. Momentum is a linear relationship. Basically, what you're doing there, Tanner, is saying mv, again, whether you think about it this way or not, you're saying mv is equal to mv, right? And that's basically what we said, except we made it in 2 steps. We didn't do it right away, right? So if you rearrange this, well, you get mt over mc is equal to a certain number, vc over vt. So when we divide those 2 numbers, okay, we get a number, okay? And then if we want to find the velocity of the car, we're going to just multiply it by vt there. So absolutely, that works. Just make sure that you have in your head straight why that works, so that sometime down the road you don't try to do some kind of crazy ratio that you don't really understand. Good? Any other questions to that? Okay. Yesterday we also, after we went through this, introduced the idea of impulse. We defined impulse as the change in momentum, not the momentum of the larva inside the shell, or not the momentum of the truck or the momentum of the car at a specific moment in time, but rather the change in momentum maybe when the truck hit the car, or the change in momentum maybe as the ball fell from a certain height to the ground level, or maybe the momentum change, the impulse, the momentum change of you as you began at rest and then sped up as you started running down the hallway to get to class on time, or something like that. Impulse is a change in momentum. And of course, a change in momentum is going to be delta P. There is an equation on your data sheet that reflects this change in momentum, this impulse, but that equation doesn't actually have delta P or the symbol for impulse in it. What is that equation? Delta P is equal to something that appears on your data sheet. What is that something that appears on your data sheet? Good. F times delta T is equal to M times delta V. So you're allowed to use exactly what it says on your data sheet. Put those 2 together if you want, that's fine. Or you're allowed to say delta P, the impulse is equal to F times T. Or you're allowed to see delta P is equal to M times delta V. We said yesterday there's 2 things that are required to change an object's momentum, right? A force and a time, and that should make sense to us. You want to speed something up or slow something down? Push on it. Apply a force. And the longer you apply that force for, of course, the bigger the impulse is going to be. F times T. Make sense? Yesterday we also did an example in class. Today we're going to do one more quick example, and then I'm going to set you free on a couple of practice questions, okay? The example that I want to do today is actually a multiple choice question from your booklet. It's on page 11, I believe, of your booklet. Multiple choice number 3. We'll do this one together, and then a little bit later on we'll have you guys work on a couple multiple choice questions yourselves. This one says, in an automobile collision, the severity of injury to the driver can be reduced by an airbag. We all know this. And yesterday we learned why that would be the case, right? Yesterday we learned that a crumple zone of a car causes the car to take longer to stop, and that reduces the force. An airbag would work exactly the same way. Causes your head to take longer to stop, which reduces the force. If the car is initially traveling at 100 kilometers per hour, right away I spotted kilometers per hour, and I know that I don't want that. So even before I've thought about the question, I've circled something that can lead to a silly mistake down the road. The airbag stops a 62-kilogram driver in 90 milliseconds. I don't want that either. Let's find the force. Okay, this is an impulse question. Clearly, it's going to be an impulse question. That's what we were working on yesterday when the bell went. That's what we were talking about the last few minutes here. It's an impulse question. But what is it that tells me this is an impulse question? I don't see the word momentum. I don't see the word impulse anywhere on the board right now. What tells me that this is impulse? Yep, Patrick? Good. There's a force and a time in the same question. Remember we identified two criteria yesterday? First one, if it was asking you for a change in momentum or a momentum gain or lost or whatever. The second one was if you see a force and a time in the same question. Here we have a force and we have a time in the same question. Let's do impulse. We know that impulse is equal to F times T, and it's equal to M times delta V. We're looking for F. We've got T, we've got M, and we've got delta V. So there is one more given we have here, actually. This is going to be VI. This is going to be M. This is going to be T. What else do we have here? VF is 0, right, because it stops. All right, so let's say F is equal to M times delta V over delta T. It's going to be 62 kilograms times delta V, which is 0 minus VI, VF minus VI. 100 kilometers per hour in meters per second. I'm not going to forget to convert that because I circled it in red to remind me not to forget that. 27.777, repeating. Thank you. Now let's divide that by the time of 90 milliseconds. I don't like these ones, man. 90 milliseconds. Okay, a lot of people will try to go scientific notation here. 9.0 times 10 to the negative 2. Okay. If you look on your data sheet, it tells you a milli is 10 to the minus 3. So let's just say 90 times 10 to the minus 3. Let's just replace the m with the exponent, 10 to the minus 3. Don't worry about putting it in scientific notation. 9 times 10 to the minus 2. Just tack on a 10 to the minus 3 onto the end of it. That way we don't have to worry about which way we move the decimal place. And is it a 10 to the minus 2 or 10 to the minus 4? Okay, just tack on the 10 to the minus 3 on the end of it. What do we get there when we do the math on that one? Travis? 1913. Okay, negative 19135.8, which rounds actually to negative 1.9 times 10 to the 4 newtons. Yeah, that makes the answer B, right? Or is it? Wait a sec, we got a negative. Where does that come into play? Did we make a mistake? What are they asking us for? Who said that? They're asking us for the magnitude. Good. So it is a negative value, but they're not asking me for the direction. They're only asking me for the magnitude. Right? Force at a time. That's what led me to impulse here. There's a lot of things that you've got to do in Physics 30 that require you to think. But there's also some things that will help us to think. Some little things that we can remember that help us to think. One of them is remember that when you see a force and a time in the same question, go to impulse. Okay, go straight to impulse every time. All right? The questions that I want you to work on for the next few minutes are on page 458. Let's take a look at both of those questions, please, and then we'll take a look at them as a class if we need to in about 10 minutes. All right, everyone, let's take a look at number 2 here. It says a dog team pulls a 400-kilogram sled that's begun to slide backward. In 4.2 seconds, the velocity of the sled changes from 0.2 meters per second backward to 1.8 forward. This is not a strange unit, like kilometers per hour or grams or something like that, but I'm going to still circle it in red or highlight it in pink or whatever I have to do to draw attention to that, because it's something that can clearly lead me to a silly mistake. One's forward, one's backward, one's positive, one's negative. What do you think the odds of me forgetting to put a negative in there for the backwards velocity? Probably pretty high. Okay? We're not all going to make that mistake, and some of us are going to make that mistake even if we circle it. But we're a lot less likely to make the mistake if we draw attention to it as soon as we see it. Calculate the average net force that the dog team exerts on the sled. What kind of a problem is this? Forget about the givens. What kind of a problem is this? Yep. Yes, and why do you say that? Yep, there's a force and there's a time in the same question. It doesn't matter whether we have both of those variables or whether we're looking for one of them. If there's a force and a time in the question, we're going to go to impulse every time. All right, so let's identify our givens here now. This is mass. This is our time. This is going to be VI. This is going to be VF. And again, we've got some things circled in red there to not forget the negatives and the positives. We're looking for the force. This is the part of the equation that appears on my data sheet. I got to use two of those three parts. Which two am I going to use to solve this question? Part 1, 2, 3. Which two parts? Yep, 2 and 3. Good. F times T is equal to M times delta V. Let's rearrange it to solve for F. M is 400 kilograms. Here's where you got to be really careful, but okay, I'm a lot less likely to make the mistake because I've already identified something in red, right? I've already identified a place where I can make a silly mistake. Delta V is VF minus VI. It's 1.8 meters per second minus 0.2 minus negative 0.2 meters per second, right? I'm not going to forget that because I drew attention to it by circling it in red. Delta T is 4.2. 1.8 minus 0.2 is not 1.6. How many people put 1.6 first and then realized they had the wrong answer? 1.8 minus negative 0.2 is what? 2. Okay. You know, here's a question that we could get on a unit test easily, right? Okay. And it's a question that we can all get correct. But it's a question where we have to all be alert for that negative 0.2. Okay, because you know it, if it's a multiple choice question, okay, the answer that you got by making it 1.8 minus 0.2, that option is going to be there, right, as a multiple choice option. Okay, so be really, really careful and don't miss that. We end up getting 190 newtons here, and it's positive, so that means it's forward. Good? Okay, let's take a look at a couple more multiple choice questions here. Number 5, first of all, which appears on page 11 or 12 in your multiple choice booklet. I got 2 of them, but you know what? We'll do them separately from one another. Let's just focus on number 5 here right now. Don't bother submitting this answer on your phones either. Just get an answer, and then we'll take a look at it as a class when everyone's done. Okay, let's take a look here, see what we got. This one says a full draw is the maximum distance that an archer can pull back an arrow. Using a recurve bow, shown below, a particular archer requires an average force of 130 newtons to pull a full draw of 70 centimeters. I'm going to circle that centimeters because I don't want centimeters, right? I always want meters. Non-standard units, draw attention to it so that you don't forget to convert it later on down the road if we need to use that number. Assuming the maximum speed of a 20.6 gram arrow, when released from full draw is 94 meters per second, the magnitude of the impulse that the bow gives to the arrow is what? What kind of a problem do we have here? Again, forget about the givens right now. What kind of a problem do we have? What's the context of this question? It's an impulse question, right? It says, what's the impulse? Okay, it doesn't take a genius to figure out that it is an impulse question. Now, we may struggle a little bit with actually calculating that impulse. That's okay. Okay, but when it asks us for impulse, we know it's got to be impulse. Let's write down some givens here now. This is going to be the force. This is going to be the displacement, how far it's pulled back. This is going to be our mass. It's pulled back from rest, so we'll say VI is 0. This is going to be VF. It's not moving when it's, before you let it go. It is moving at 94 when it's released from full draw. And we're looking for the magnitude of the impulse. We're looking for delta P. So we've got 3 parts to the equation, 2 of which appear on our data sheet. F times delta T is equal to M times delta V. Which 2 of those 3 parts are we going to use? 1, 2, 3. Liam? 1 and 3. We've got m and delta v, or vf and vi, and we're looking for delta p. So let's say delta p is equal to 0.0206 kilograms, or you could say 20.6 times 10 to the minus 3. Multiply that by 94 minus 0. When we do that math, what do we end up getting? 1.936. So 1.94. Now, I forgot to mention this when we took a look at your practice problems in the last little group there. You see kind of a strange unit there that you don't recognize for impulse. What would you think the units for impulse would be? Change in momentum. The units would be kilograms meters per second. Do you think you could still use that? Sure you could. But a Newton second is exactly the same thing as a kilogram meter per second. That comes from the equation, right? Delta P is equal to F times T, M times delta V. M times delta V gives you kilograms meters per second. F times T gives you newtons times seconds. So either one is fine. They mean exactly the same thing. There's no conversion to do. Okay, so you see that? Impulse, kilograms meters per second. It's also impulse. How many people got 1.94 there? Good. I want you to do question number 6, but I want you to submit this one on your phones, okay? So let's submit this as multiple choice number 1. Just go to my website, click on that link again, or hopefully you have it bookmarked already. Do question number 6 real quickly, submit it, and then we'll take a look at how many people got it right. Sorry, number 4, I should say it is, number 4. Take a look at how many people got it right and how many people got it wrong. Well, let's take a look here. It says the SI units for impulse. What does SI mean? It's the metric system, right? It stands for System International. Okay, it means basically the metric system. What are the metric units for impulse? Well, we just talked about that. We have a couple different units that we can use for impulse. One is that Newton seconds, that new one that we just learned, comes from F times T. The other one comes from M times delta V. Which one is it? According to 90% of you, it's B. 5% of you said C. And then 5% of you said E. They weren't sure. The answer is B. Hey, my recommendation in a question like this is don't memorize that. Okay, by the end of the year, we're going to have learned so many different quantities and so many different variables and units. Don't memorize the units. Okay, if you happen to remember them off the top of your head, that's great, but don't try to memorize them. Look at the equation and figure it out. The impulse is equal to m times delta v. This is kilograms. This is meters per second. Not meters squared per second, but kilograms and meters per second coming from m and delta v. Does that make sense? Good. We're going to move on here and talk about 2 qualitative implications of impulse now. We've done the math, and we'll do more math, but we're ready to move on to talk about the concept, kind of bigger picture than just mathematics of impulse. Impulse is a pretty important topic in that it addresses 2 very, very big real-life scenarios. Okay, the first one is when we have what we call a predetermined impulse. A predetermined impulse is an impulse that's going to be the same no matter what. A car is traveling down the road at 100 kilometers per hour. It has a certain mass. It therefore has a certain amount of momentum. That car will stop. We know that. That car will stop. We don't know how it's going to come to a stop. It may come to a gradual stop at a stop sign, or it may come to a crashing stop against another car or against a concrete wall. But that car will stop. If that car has a mass of, let's say, 1,000 kilograms, and it has a velocity of 10 meters per second, then it has a momentum of 10,000 kilograms meters per second. It will have a momentum sometime of 0, it will experience an impulse of 10,000, no matter what, no matter how it stops. Make sense? That's a predetermined impulse. We can't control what the impulse of that car is going to be. This is its momentum. It's going to be 0. Okay, the impulse is predetermined. Now, in a situation where you have a predetermined impulse, the idea is that you usually want to increase the stopping time. Think about that. When you're coming to a stop in that car, do you want to crash into a wall and stop really, really quickly? Or do you want to put your foot on the brake and gradually come to a stop? You want to gradually come to a stop, right? Okay, if you're driving your car and you are in an accident, God forbid you are in a car crash, do you want to hit your head against the windshield or the steering wheel? Or do you want to hit your head against the airbag that causes you to take longer to stop? The airbag, right? If you're catching a baseball, do you want to catch the baseball like this, hold your hand out like this, and don't move it at all? Or do you want to kind of cradle that ball a little bit, like this? Yeah, that's exaggerated, obviously, but do you want to cradle it a little bit to increase the time that it takes the ball to stop? Okay? We know intuitively, even if you're not a baseball player, that you want to cradle a little bit. Okay? Even if you're playing hockey, okay? When you're taking a pass, do you hold your stick rigid like this when you're taking a pass, or do you kind of cradle that pass a little bit? Increase the time that it takes the puck to stop. Every time we want to increase the time that it takes the puck to stop. Why? Because what that does is decreases the force, and it's the force that really matters here. We want to increase the stopping time, decrease the force. I'll show you some numbers in there just to illustrate this mathematically here. Okay, our impulse is equal to F times delta T. Let's say that our impulse is 10, and it's predetermined, so it's going to be 10 no matter what, no matter how we stop the object. Let's say the force is 5. What's my time got to be? What's my time got to be? 2. Okay? Let's say that now my impulse is 10. Let's increase the time that it takes to stop. Let's increase the time that it takes to stop till, let's double it, 4 seconds. What does F got to be? 2.5. What have we just done by increasing the time, by doubling the time that it took the object to stop? What have we done to the force? We've cut it in half, right? By increasing the stopping time, we've decreased the force. Does that make sense? We just watched the Cirque du Soleil video of the guys jumping on this mat and the guys jumping on each other's shoulders. We saw that when they jumped on each other's shoulders, they bent their knees. Okay, that increased the stopping time, decreased the force. We saw that when we jumped on the mat, they actually held the mat in the air and then dropped it as the guy was hitting it. Increase the stopping time, decrease the force. When we have an impulse that's already determined, okay, we increase the stopping time, we decrease the force. Now, there is one more scenario that we talk about as well. I don't even know if this is a word, but I'm going to write it down. When we have a non-predetermined impulse, I don't think it is a word. I don't think you can hyphenate a word twice, can you? We're going to say that that's the word anyways. A non-predetermined impulse. A non-predetermined impulse is when you can control the impulse that's given to an object. Typically, you have a predetermined impulse when you're stopping an object. You have a non-predetermined impulse when you're starting an object. A golf ball is sitting on a tee. You can give that golf ball a little bit of impulse or a lot of impulse, depends on how you hit it. It's not a predetermined impulse. Okay, you control how much impulse it gets. A hockey puck, okay, you control how much impulse that puck gets and therefore how fast it goes. A baseball, the same thing. When you're hitting it, you control how much impulse that baseball gets. Even when you're pitching it, you control how much impulse that baseball gets. Some people pitch the ball faster than others, okay, which means that they've given the ball more impulse. When you're starting an object, that's when we have a non-predetermined impulse. The idea here is that you increase force and or time, and that's going to increase the impulse. I'm not a very good golfer, but I'm okay, I guess. I'm not great by any means, but I'm okay. Okay, I know enough that if I want to hit the golf ball fast and therefore far, I need to do two things. One, I need to hit it relatively hard. I need to apply a relatively big force. Okay, if delta P is equal to F times T, and delta P is not predetermined, then a bigger force will give me a bigger impulse. What else gives me a bigger impulse? A bigger time of contact. And that's why I follow through when I golf. That's why I don't just do this. When I follow through, okay, what does that do? It increases the time of contact between the club and the ball. That gives me a bigger impulse. When you hit a baseball, what do? You follow through. Okay, it's all form. Part of its strength, obviously, the bigger force, bigger impulse. But there's so much of it that's form, proper technique, increase the time of contact, increase the impulse, make the ball go farther, make the ball go faster. Make sense? I'm going to show you another little video here right now to show you one of the applications of this, kind of the real deal.